Elements in column 18 are noble gases. So that very last row furthest on the right of the periodic table are noble gases. They are called noble gases because they are very stable and unreactive. And the reason for this is because they have 8 valence electrons. So neon electron configuration is 1s2, 2s2, 2p6. Krypton is in row 4, so krypton ends in 4p6. So all noble gases are going to end in p6. And we can use this to abbreviate, shorten what we need to write down for electron configurations. You use the noble gas configuration as a base. So argon's configuration is 1s2, 2s2, 2p6, 3s2, 3p6. Calcium's configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So calcium's configuration is the same as argon's configuration. There's argon's configuration right there with 4s2 tacked on the end. And so when we're abbreviating calcium, we do it as argon in brackets and then 4s2. So what we're basically saying is I have the configuration of argon, so I have everything from 1s through 3p in this bracket, plus whatever else I need to finish out the electron configuration. So when you are writing abbreviated electron configurations, you will find the noble gas in the row above the given element. So it's always the row above. You're going to write its symbol in brackets and then add electrons into the proper orbitals until the total number of electrons is reached. It's really important to make sure that you do start after the bracket with the correct orbital. So all noble gases end in P6. And if you look at the electron placement diagram, after P always comes S. And so you always start after the brackets with whatever the next S is. So francium has 87 electrons. It is in 7s. And so when I go up a row and go over for francium, I get radon as what I'm using to abbreviate. Radon ends in 6p. So what I'm saying is in this bracket, I have everything from 1s through 6p. So after the bracket, I have to write what comes next. What comes next after 6p following that electron placement diagram is 7s. Francium is in the first column of the S block, so francium is 7s1. Alternatively, you could think about it as radon has 86 electrons, francium has 87, so you need one more. So this, you don't need all the extra stuff. This right here is the abbreviated configuration for francium. Platinum is atomic number 78. Platinum ends in 5D. So going up a row, going all the way over to the noble gases, I see I use xenon to abbreviate platinum. Xenon ends in 5p. So following my electron placement diagram, after 5p comes 6s, then 4f, then 5d. So fill up my S. F's are full with 14, so fill up my F. And then platinum is the 8th one over in the row of 5D, so it's 5D8. Or you could add up this, and you would get 70, because xenon's 54. So 54 plus 2 plus 14 is 70, and so you need 8 more to go into the 5D. Arsenic is atomic number 33. Arsenic is in 4p. Going up a row and going over, we see that we use argon to abbreviate arsenic. Argon ends in 3p. Following the electron placement, after 3p comes 4s, then 3d, then 4p. So we fill up the S, we fill up the D, and then arsenic is 4p3. It's in the third column of the P block, or you could add up. This is 30 total, because this is 18. So you need 3 more. So that's abbreviated configurations. Ion configurations. Ions form when atoms gain or lose electrons. And so a neutral sodium atom has 11 electrons. Sodium with a +1 charge got that charge because it lost an electron, so a sodium ion has 10 electrons. So when you're doing the electron configuration for the sodium ion, you don't look at sodium's placement in the periodic table because it's lost an electron, so that doesn't match up anymore. You just do the configuration for 10 electrons. So 1s2, that's 2 electrons. 2s2 is 2 more, so that's 4. So 2p6 is what I need to get to 10. I'm going to change this to phosphorus, actually, the phosphide ion. So a neutral phosphorus has 15 electrons. A phosphide ion, therefore, has 18 electrons. So, again, just do an electron configuration for 18 electrons. 3s2, 3p6 gets me to 18. Oxygen also has 10. Neutral oxygen has 8, so we've gained 2 to get my -2 charge. So 1s2, 2s2, 2p6. So oxygen and the oxide ion and the sodium ion actually have the same electron configuration, and that's not a coincidence. If you notice, all these ion configurations end in p6, just like noble gas configurations do. This is because ions form to get a noble gas configuration. Noble gas configurations are the most stable configurations, and so atoms, when they form ions, they do so to have the same configuration as a noble gas. This is called being isoelectric. So isoelectric means that it has the same configuration. So if I'm looking at 5 ions that are isoelectric with krypton, really what I'm looking at are 5 ions that are going to have 36 electrons because krypton is atomic number 36. So that's going to be the bromide ion, because bromine's 35, it gains 1, gets a -1 charge, so that's 36. That's going to be the selenium ion, selenide, I guess, and then the arsenic ion, arsenide. Going on the positive side, rubidium is going to lose 1 electron. Rubidium's number 37, so it loses 1, it gets to 36, and then strontium loses 2 to get to 36. So those are my 5 ions that are isoelectric with krypton. Electrons can be classified as either core electrons or valence electrons. Core electrons are the inner electrons, and valence electrons are the electrons in the outermost energy level. The valence electrons are really the only important ones because they determine an atom's properties. Since valence electrons determine an atom's properties, atoms that have the same number of valence electrons have similar properties. So looking at the electron configuration of boron, boron's highest energy level is 2. And in that second energy level, I have 2 electrons in the 2s and 1 in the 2p. So boron has 3 valence electrons. Scandium, highest energy level is 4. is 4. It's not always the last one, right? It's just whatever the highest number is. So scandium's outermost energy level is 4. And in that 4th energy level, it has 2 electrons. So scandium has 2 valence electrons. You can show valence electrons using something called dot diagrams. So the electron configuration of phosphorus is 1s2, 2s2, 2p6, 3s2, 3p3. So the highest energy level of phosphorus is energy level 3. There are 5 electrons in that energy level. So when I'm doing the dot diagram of phosphorus, you just put the symbol, and then you place electrons around, top, bottom, left, right, until we get to 5. So just like with Hund's rule, you're going to do 1 per side first. So 1, 2, 3, 4. And then you pair up. And it doesn't actually matter where you pair it up. I always just start at the top and go clockwise. Bromine, I'll do the abbreviated one here, is argon, 4s2, 3d10, 4p5. And so when you do an abbreviated configuration, you can still see the valence electrons because those are always going to be on the outside. They're the highest energy level. So those will be outside of the abbreviation. So bromine's highest energy level is energy level 4. I have 2 in the 4s and 5 in the 4p, and so I have 7 valence. So when I'm doing the dot diagram, 1, 2, 3, 4, 5, 6, 7. Lastly, calcium. Calcium you also abbreviate with argon, 4s2. So calcium only has 2 valence electrons in that 4s sublevel. So calcium only gets 2 dots. It doesn't matter if you put the 2 dots like that, or if you do one on the top and one on the bottom, as long as you have 2 separate dots. There is a pattern to valence electrons because of the way the periodic table is set up and the way that electron configurations work with the periodic table. So the elements in groups 1, 2, 3, and then, 1, 2, and then 13, 14, 15, 16, 17. This was an old numbering system. And 18 are sometimes called main group elements or representative elements. Elements in the same group always have the same amount of electron configuration, or elements in the same group always have the same amount of valence electrons. So for example, everything in group 5 is going to have something S2P3. It might be 2S2, 2P3, 3S2, 3P3, but it's always going to have S2P3. It's always going to have 5 valence electrons. So this is our pattern for our representative elements with valence electrons. Everything in group 1 has 1. Everything in group 2 has 2. Group 13 is 3, 14 is 4, 5, 6, 7, 8. So if we were to look at dot diagrams within a group, they would look very, very similar because they all have the same number of valence electrons.